Okay. All right, let's give this a shot. Oh man. All right, so this is gonna be crazy. Um, Action Lagrangian. I'm gonna try to do it from a few different angles, kind of like at once, just to see what all the different perspectives say. The idea of constraint based on possibility is kind of a really cool um, way of looking at it. So, right, so the idea that, um, and forget the Newtonian, just for now. Um, there's two separate worlds, though. Like there's the deterministic, and then there's the probabilistic. Obviously, the probabilistic ends up being quantum, right? Um, and I'm wondering how like quantum electrodynamics and quantum field theory come, but we can address that later. The deterministic is Newton and GR, relativity, or even special relativity, right? So, which is cool because the point is that these have an action, right? That is the integral technically between 2 points where everything is known where it is. The difference between these two, of course, is here space-time is fixed. Newton space-time is fixed. GR space-time is dynamic. But other than that, it's actually the same thing. We know locations. There are coordinates, right? Uh, we say like what, xi dot for the velocity and the time. So what we do is we add up, right, this parameter that represents, right, what is happening and kind of like this concept of constraint, right? So what I want to look at is this, right, this is like the history, right? This is like the history, right? This is like what is possible or what is like happening minus constraint. It turns out for GR, that's all one thing. That's the space-time interval. For Newtonian, that ends up being kinetic minus potential energy. So it's actually pretty straightforward, right? So for Newton, this ends up being the integral, and I'm just gonna forget the limits. I don't like including this. And for GR, well, there's actually two of them for GR. For space-time itself is different from a particle path. I'm going to do like a particle path, right? So for a particle path, right, action is just the space-time interval. It's just that. Now, I think we might have mass involved there, right? Maybe, right? But that's just a multiplier. Conceptually, it's just the space-time interval. What I'm hoping to outline here is why and what connects this this with the quantum version. In other words, what connects all of them, right? And it's kind of this idea of like possibilities versus like constraint. That's what it's all about. It's possibilities versus constraint. That's the whole theme here, right? Right? We have possibilities versus constraint. This is existence. And realizing that this is existence is huge. When you start to see things like forces as like bookkeepers of constraint, right? Um, how a path is sort of not just chosen, but it couldn't exist any other way, right? Ends up being kind of the way to look at this. So, and you can realize this in any situation. Um, so one thing that I've missed last time that was huge is yes, we want to assume an outcome. There's an answer, right? Which is like, what's the answer? Here, the outcome is a path, right? X of t, right? Or xi of t, right? It's like there's a position in time that it's moving, right? So we have this outcome, right? So, and we can say, okay, which outcomes are possible, which are not. In quantum mechanics, the outcome is the wave function, because we're not talking about measurement here. We're talking about the evolution of the wave function in quantum mechanics, right? So the outcome here, we know the positions, it's deterministic, right? We know that there is a position x, I, x, there's a velocity and there's a time t. We know that, which means our action had better depend on those variables, right? And it must add up every little thing of those, right? This is the information of what is happening minus the constraint that kind of scores what's possible and what's not. And we add it for every moment locally. It has to be additive, it has to be local. It doesn't have to be. The universe doesn't have to be that way, but we kind of observe the universe is that way. So our models, Newtonian GR, are modeled off of that. They are modeled off of local interactions. In this case, it's local space-time curvature. That's general covariance, right? It's there's this continuity of space-time. Here, there's a continuity of motion, right? So ultimately, I'm going to outline the Newton and the GR assumptions, but I just wanted to sort of give an overview of how these are kind of saying the same thing, right? In the probabilistic version, this takes a little longer to explain. I'm just going to sort of like going to sort of like write it that for quantum, it ends up being like uh, let's put it this way. Um, in other words, like, okay, classical is like there's one path. Probabilistic nature of quantum reality says uh like the universe explores all paths weighted with phase, otherwise known as action, which means it's like the we have to talk about how a wave function is symmetrical in a formation like this. This is called the phase, right? I'm not going to get into that, but it's the idea that I believe we can call this I don't exactly know what this A is. Um, whether this is like the ends up being the ultimate result or it ends up being what's called the amplitude, right? Is the sum of all possible paths, right, of e to the I action over h bar. So we add up all the possible things. This is called taking a path integral. Path integral says let's add them all up. Let's add them all up, and the sum of all of them, most of them are going to cancel out, and we end up getting kind of a probability distribution of what can happen. This is different from measurement, right? This is actually something called decoherence, when you have a lot of possible things that cancel and you end up getting one thing. What's cool about this is that there's a connection, when the action is much bigger than Planck's constant, you end up getting that classical reality emerges. We can actually show that this leads to this. We can actually also show that this leads to the Newtonian approximation as well, that all of these are actually the same, or that this and this lead to this, which is kind of cool. Anyway, I don't want to clutter this too much or talk about things that I don't fully understand yet. So let's move on to uh, the next thing. So I'm actually going to say one thing about quantum first, and then I'm not coming back to it. So quantum mechanics can be sort of said in a really, really cool way, and that's this. So from path integrals, we can actually derive Schrödinger's equation, which I don't want to do because that's actually really complex. But let's just say we know that what's called an wave function, an eigenstate, right, is it propagates, meaning it evolves according, and this ends up confirming the Schrödinger's equation. This is the initial state, and this is obviously the final state, right, of t, function of t. It evolves by this, right? And energy times time ends up being what's called the phase. Now, this is cool. What happens is like the wave function kind of spreads out over time. So, classical mechanics, uh, or GR, says that the action is the integral of the Lagrangian dt. Instead, quantum mechanics says the phase, right, is equal to action over Planck's constant. Now, you'll notice that the unit of action is energy, joules, times time, seconds. You're adding up joules, which is a great like bookkeeper of information, right? This is information. So this is kind of saying information stays constant over time, right? Planck's constant also has the unit of joules times seconds. So Planck's constant you can see is the minimal action anything can have. It's quantized action. Right? Which is a really cool way of seeing Planck's constant, right? Or at least in this case, the reduced Planck's constant. So um, the amplitude for a process is a sum over all the possible paths. And sorry, this is the amplitude for a process. Indeed, A is for amplitude, is the sum over all the possible paths uh, where, right, we have um, e to the I s over h bar, right, for each path. And s is different for each path, right? We have a different action for each path. Formally, it ends up looking something like this. You end up getting like the evolution of the wave function ends up corresponding to some, uh, some function that depends on distance, right? That is kind of like your situation, right? Times this. This ultimately ends up being, right? And S ends up being a function of position, right? Which is a function of time. So your action for each position, right? And the question ends up being, what's this function? So if action ends up being much bigger than h bar, right, then the phases cancel. And that requires understanding this, right, to understand what I mean by that. And so they destroy each other. So what you end up getting is that you get the classical stationary action from this. This is the classical limit. If that made no sense, that's okay. The point is we can show this later. I just wanted to show you kind of the result, and I need to remember what this actually represents. So classical mechanics is the stationary phase limit of quantum mechanics, which means it's like, oh, you have these really large values of action. In other words, big scale. What ends up happening is that most of these ends up canceling, and you end up getting essentially that ds equals zero. Just showing you that's kind of where we can go. Let's come back now, though. Again, if that made no sense, that's fine. We can go over that. We don't have to, though. So let's review what action is. I'm sorry if that last part didn't make much sense. It's okay. Um, so let's go back to classical and NGR, like determinist, right? So it's this, right? The integral of L dt, right? So again, the outcome, right, is like a path, right? Right? A path through space and time as a function of time, right? It's like a string of local points, right? Uh, we have symmetries, right? Like a shift in coordinates, right? Doesn't change the path, change the outcome. Meaning there's no, for example, there's no preferred position. There's no preferred starting time. I can start at any time I want. And there's no preferred orientation. Those are the three classic ones. There ends up being no what's called voltage, right? It's called a gauge. I mean, this is gauge symmetry. And we can talk about that. I'm really kind of eager to get into that. Is that there's no voltage equals zero. You can set that to anything you want and you still get the same outcome. This ends up being conservation of charge. These all produce conserved quantities that are represented by this. So the whole point is like this shows like what is possible and what is conserved, what is invariant. So the action does more than just like the metric. It does more than just Newton's laws. It's equivalent to them. You can actually derive Newton's laws from or principles other than this that are the same as the derivation of this. But in doing so, what you're missing are the invariants. So this is more holistic than Newton's laws. Basically, they live parallel, but you're actually limiting yourself and you actually have to make a leap at some point to fully derive Newton's laws. Sorry, I didn't mean to say you can completely do it, but you can kind of sort of get there without action. This is more holistic, is why this is so very valuable. So, right, so it needs to be local and additive. That's huge. So it's the global, like adding up integral that's additive, right? um, which like it codes the consistency, right, of all the segments, right? This is all a string of local points together, right? So if it's stationary, careful, not minimum, just stationary, and don't think of this as a function. Think of this as a measurement of consistency. If it's stationary, then what it says that any deviation or change in this is inconsistent. We need this to be the true invariant of existence. Action is the true invariant. Because if it's a measurement of consistency, the definition of consistency is that it doesn't change. The definition of inconsistency is that it does change. So don't think of it as like a math function. Think of it as like this is representing that which is consistent with all global things added up. And therefore, if I change it, if it's stationary, sorry, if I don't change it and if it's stationary, that respects global equivalence. And ds not equal to zero literally means that the path is inconsistent with our model of reality. model meaning the constraints, meaning the symmetries, meaning like all the assumptions we're making about reality. So it's a global pattern of relationships, not just like a number. It's like more powerful than that. So cool. I hope that made more than 0 sense. So this is really cool. I'm gonna help make this a little make a little more sense. So like what action is, right? So if you have, we need something that is invariant, like under like symmetries. We need something that is applies to a global like history and evaluates constraint versus possibilities. That's what action does, right? So, for instance, if we have some sort of like transformation, like say a time transformation or a space transformation or an angle transformation, right? Et cetera, right? Or like I said, a phase transformation for quantum mechanics. And we'll talk about what that means, right? We need like the action, that's an S, right? Uh, to remain invariant. We need it to remain unchanged, right? So for any general coordinate, right, xi going to like some transformation, right, xi of time, right, we need the action, which is a function, right, of that, right, equaling the same under any transformation, right? We need to make sure that it codes, right, true invariance. Like action is the true invariant. Quantity or right, that encodes, right, truth, right? That encodes the outcome, like the only possible outcome. Like we need it to encode the constraint and possibility map. It turns out the Lagrangian does that. The Lagrangian does that, and we can figure out this Lagrangian for every model. I hope this makes more than 0 sense, right? So from this, really cool things can emerge, right? So once we sort of see what action is, again, fundamental assumptions behind action, determinism, and of course, this is still classical and relativity, right? Locality. We need it to add additivity, right? We need it to be like things are accumulating over like little bits, right? We need it to be coordinate invariant. No matter if I switch coordinates, I switch reference frames, it's the same, right? I need it to be the same and I need it to be continuous. Obviously, we need it to be self-consistent. All of this is like self-consistent, right? We live in a self-consistent universe, otherwise existence wouldn't happen. So therefore, the most general object you can build that is this, right, is this. In classical mechanics, and it ends up being the space-time interval. And I think there's an MC in there, and I think there's a negative sign in there for general relativity. These are the simplest objects you can build. I'll make other videos that kind of show that. What I'm doing is a general overview here now from this, like from, and let's go to Newtonian, right? from our action being the, T1 to T2 Lagrangian xi dot t dt, we can then say, okay, let's have some xi of t moving to something that shifts the path a little bit, like some little eta function that is multiplied by some like small change or even a big change. Doesn't matter. It's a change, right? And this is a deviation. What happens is then eta of t1 equals 0, eta of t2 equals 0, because I imagine we have this path that's consistent and I make this eta, right? Eta of t be at t1 and t2, right, equal to 0, right? And I'm actually wondering how this corresponds to this. Maybe the path, sorry, let's make it go like that. So t1 and t2 are actually from the beginning. That actually makes more sense. So here's my xi of t that I'm testing. Is this consistent? And let me change it. And so this deviation, right, obviously has no, we want it to match 0 at the beginning, right? We want it to match x of I, right? This deviation is epsilon times eta of t. Cool. So from this, what we see is that you can end up showing that ds is this, the integral of t1 to t2 dl sorry, I'm using x's, dxi, and that xi could be xyz in Cartesian, it could be r theta phi in spherical times eta plus dl dxi dot eta dot. Go through that, see if you can prove that pretty quickly. Now you can follow the math, right? Integrate by parts, and you get this, right? So sorry, not both. Integrate the second term by parts, and you end up getting that this, the integral of that, right, equals dl dxi dot times eta evaluated t1 to t2. Obviously, you're integrating that one first, and then you're subtracting the d dt, sorry, on the inside, of course. Integral of d dt of dl dxi dot eta dt. So integrating this by parts, we get this. This is 0 because eta evaluated at t1 and t2 is 0. This is left over, and we end up getting that ds is the integral from t1 to t2 of dl dxi, right? And eta is just in front, right? Or I guess it's in there. Minus d dt of dl dxi dot. And this, of course, equals 0 is the Euler-Lagrange equation. And we just derived it. From this, you can get F equals ma, E equals mv, and the energy equals T plus V. And we can do that in the next video. I think this is a good place to end.